All right, everyone. Thanks for coming. Good morning. My name is Daniel Chambers, and I'm a developer at Liberty Financial. My roots are as a .NET developer, having worked on projects in both C#, F#, and JavaScript. And I've also spent a year or so writing Haskell in production, and that was a lot of fun. So I joined Liberty Financial last year in order to help them upskill in functional programming, in particular the F# language. And one of the things that struck me when I first started teaching the team at Liberty about F# and functional programming is how much assumed knowledge there is and that one builds up over time and takes for granted. Although I too started learning FP after having already learned imperative object-oriented programming, I'd forgotten how unfamiliar FP techniques and jargon are to those who have never explored the space before. And this is what has prompted me to make this talk, to help decode and explain some of the very basic terminology and jargon that you'll encounter when you first start out in FP. Now, one of the first questions I got asked by a curious product manager was, what is functional programming exactly? Well, functional programming doesn't usually refer to an exact concrete definition. Like object-oriented programming, it refers to a set of programming techniques and ideas that are all related. So different languages will implement more or fewer of these ideas. But there's a few basic tenets that I think we can all agree on. Eric Meyer once referred to functional programming as a style of programming where expressions are more important than statements, and I think that's a really good place to start. In FP, you always write code in terms of expressions that return a value, as opposed to statements that don't return anything but perform some sort of side effect. This style of programming allows you to write programs in a declarative compositional style. And a great example of this is the fundamental if-then-else language construct in F#. It doesn't behave like a regular if-then-else like you'd find in a language like C#. Instead, it behaves more like C#'s ternary operator. It's an expression and it evaluates to a result that you can assign to something, as opposed to two branches that perform two different side effects based on what your condition is, like a regular C# if-then-else. Another must-have in FP are first-class functions. And this is where we treat functions the same as we treat other values in the language, like strings and integers. We can give them names, we can pass them to other functions, and we can return them from functions. And functional programming is all about combining expressions into functions and functions into wider programs. The other major tenet of functional programming is purity and the elimination of side effects. And this means that an expression in your code, when given the same inputs, should always return the same value. Some FP programming languages encourage purity but allow impure and side effectful code, while others disallow impurity entirely and force you to write 100% pure code. Now, you probably looked at that last slide and went, you've already started with the jargon, and we're only 2 slides in. Unfortunately, jargon is hard to avoid. In fact, all of us object-oriented programmers are already steeped in our own fair share of jargon. We've got objects, classes, interfaces, methods, overloading, variables, attributes, iterators, decorators, strategies, factories, and if you're very unlucky, abstract service factory builder bases. Jargon is useful. Jargon is a shared language that allows speakers of it to communicate complex ideas concisely and precisely. However, with all things, there's always a downside. Jargon makes it harder for newcomers to understand some things until they learn to speak that shared language. Now, FP is a different paradigm to object-oriented programming, and it has its own set of jargon. Bindings, purity, impurity, referential transparency, immutability, currying, partial application, algebraic data types, sum types, product types, folding, tail calls, and much more. And look, just like we all learned that imperative OO jargon, we too can learn FP jargon. So we're going to walk through all of that basic FP jargon and probably pick up a little bit of F# along the way. So in functional programming, data is immutable by default. In some languages like Haskell, there's no mutability allowed at all. Immutability means that when we construct data, we can't change it in place. The only way to effect change is to make a copy of the data with your changes made to it at copy time. And this means data in FP behaves like instant strings do in C#. And this can sound difficult to work with, but in practice it actually simplifies things. Immutability makes it much harder to make tangled messes that we've all seen rampant mutability allow. In F#, we can define record types, which are an immutable data type that has a number of properties. And you can see the syntax for defining the movie type up on the slide. It's got 3 properties: name, year, and studio. Now we can construct an immutable value of the movie type by using the curly braces and assigning a value to all properties. Now it's not possible to make a half-initialized movie value. Because it's immutable, there'd be no way to set the rest of the properties after construction to finish initializing it. We must assign all the properties. Now when we want to change that movie object, we can use the curly braces again, but this time we put down the name of the value that we want to copy. So in the case up on the slide, we're using Infinity War, and then we're using the with keyword and assigning any properties that we want to change. Any properties that we don't put there, such as studio, are copied from the Infinity War value as is. And this is very useful because it means we don't have to manually list all those other properties, then update that code every time we add new properties to that movie type. Now, is all this copying inefficient? In some cases it can be. However, there are many data structures, techniques, and technologies that can be used to make immutability efficient. An immutable list is a really good example of a data structure that seems like it would be inefficient on the surface. If we had to copy the whole list every time we wanted to add something to it, that'd be very expensive. C# lists do some copying behind the scenes as they grow their internal arrays, but most of the time when you're adding something to one, you aren't copying the whole array and you're just mutating a pre-allocated array element, and that's quite efficient. In FP, immutable lists are created using a linked list data structure, and this means they can be both immutable and can allow cheap additions to the list. Let's see how that works. A linked list is actually made up of 2 things: a single item plus a reference to the rest of the list. So when we start with a list of 1, the rest of the list reference is not pointing to another list because it's just a list of one thing. And you can see the syntax that F# uses to create a list up on the slide. It's the square brackets. So when we went, let's add one item to that list. So we're going to add a B to it to make a list of 2 things. And in F# we can do this using the cons operator, which is that double colon operator. It takes the item that we want to add on the left and then adds it to the list on the right-hand side of the operator. And you can see from the diagram that we've now made a new list with its item part containing the B, and the rest of the list is pointing to list of 1. Notice how list of 1 hasn't been mutated at all. It's still the same, but we've reused it inside our list of 2 without changing it. It remains immutable. And we can do this again, this time adding a C to make a list of 3. And again, list of 2 is not mutated. List of 3 simply points to list of 2 for the rest of the list. And creating a list of 4 is exactly the same. Each list reuses the nodes from the previous list inside itself and doesn't require copying the entire list. And this is how we can have immutability and efficient lists at the same time. Lists are basically turtles all the way down. Now, because everything is immutable, we don't have variables in pure functional programming. Variables imply their values can vary, and immutability will prevent this. In FP, instead, we have bindings. A binding binds a name to a value. So up on the slide, we can see a couple of F# bindings where we're using the let keyword to bind the name, first name, to the value of Steve, and the name, surname, to the value of Rogers. We can also use bindings to define functions. We can see on the slide that the concat name is bound to a function that takes 2 parameters, first and second, and the function body will concatenate them together. Now this could be expressed as a regular let binding by using a lambda function instead. So in F#, the fun keyword and the arrow are how we define a lambda function. So you can see how this now looks very similar to the original let bindings. We've got let, the name, equals the value, which is a function. Pure and impure functions are other pieces of jargon that you'll hear talked about a lot when it comes to functional programming. A pure function is one that, when given the same input, will always return the same value every single time. As a contrast, impure functions, when given the same input, might produce something different. This reproducibility of pure functions makes them much more easy to reason about. Pure functions also don't mutate their input values, but impure functions might. And this means pure functions can be used safely, whereas impure functions have to be treated a little bit more carefully because they might unexpectedly modify what you're passing to them. Purity and immutability go hand in hand. pure functions can't mutate anything, but they can calculate new immutable copies of values and return them. Pure functions cannot depend upon a global mutable state, since this might cause them to change their output given the same input values, since the global state might have changed and now they make a different decision. Impure functions have no such restriction, which makes them much more unpredictable. And all this means that pure functions are much simpler and easier to reason about. They behave predictably and reproducibly. In contrast, impure functions may not. To understand how they will behave, you have to understand their inner workings. And if they depend upon some shared mutable state, you need to understand all the other code that shares that same mutable state in order to figure out how that whole mess will interact. As I'm sure we've all encountered at some point in a code base somewhere, when this is done poorly, it becomes a nightmare to debug and to change safely. Now, this reproducibility and simplicity of pure functions makes them trivially easy to test. You simply pass in your input parameters and assert your output. There's no need for complicated mutable state to mock, manage, and reset between test runs, which can often be the case with impure functions. So let's look at an example of a classic impure function in C#. This add family members function will take a family and mutate the mother and father properties on it. It also mutates the children list on the family to add a few extra children. It then returns the same family object as was passed in, probably to help with some sort of fluent style syntax. Unfortunately, this makes it look like it might return a new family, but you're not really sure. You'd have to look at the implementation to see that it actually doesn't. It just returns what you passed it, but it's mutated it. So really, it'd be better if it returned void, because then it'd be obvious it'd be doing a side effect, but then you probably wouldn't get your nice fluent syntax. So what does a pure version of this function look like? Turns out it's very similar. But instead of mutating the input family, we use F-sharps with keyword to make a copy of the family, and then we change the mother, father, and children properties to new values. The children property gets a new list that immutably adds to the existing children list using that double colon cons operator. So here's another example. We've got a new transaction function that takes an amount. It returns a brand new transaction, but it reads the current time from datetime.utcnow. Now, utcnow is a global mutable variable that is constantly changing as it tracks the current time. This function also reads the current user off some global user context. Now, given the same input, which would be the same amount value, this function will always return something different and therefore is impure. It'd also be pretty hard to test because date created would always end up as a different value, and the user property would require to set up some global current state before calling the function. Otherwise, you'd end up with a null reference exception. As a contrast, here's the pure version. Instead of reading the global state in the function, the pure version of the function takes that state as arguments, and then when we pass that same input, we always get the same result. But up at the top of your program, near where you do your I/O, probably in your API controller or somewhere similar, you'd read your global state like the time and the current user context, and you pass it into your pure functions. That means all your pure functions are now very easy to test, because given the same input values, you always return the same thing you can assert against. There's no global state making the return value of your functions a moving target. Now, purity, immutability, and bindings give rise to a concept called referential transparency. Now, referential transparency is where you can substitute a binding name for its value and the program still remains the same. The name and the value are effectively interchangeable because the value can't be mutated and the name can't be changed to point at a different value. Now, we can use referential transparency to reason about our program and effectively execute it by replacing names with values. So let's try that out when creating a full name binding. So we're going to concat the first name and surname values. The first substitution we can do is to replace that concat name with its value. So we can literally just replace concat with its value, which is that function. So the next substitution we can do is to call the lambda function by basically just replacing its parameters with what's being passed as arguments. So we're going to replace first and second with first name and surname. Then we can substitute the first name and surname names with their values. And finally, we can execute our plus operators and get our final string. Now, referential transparency is very useful when refactoring because it makes it very, very easy to extract parts of functions out as named values, whether they be concrete data values or other functions. And we can do this safely because we know referential transparency means that the refactoring is simply a rearrangement of code and it doesn't actually change the behavior of the code. So let's see a contrived example. Here's some code that's up on the slide that we all don't understand, including myself. But thanks to referential transparency, we kind of don't need to. I don't need to know what all those functions do under the covers and what all the values are. I can extract any expression out from that piece of code and give it a name and it won't change the result of this program. So let's say I want to extract this big chunk out in the middle and give it a name. I can rip it out, give it a name, say extracted thing. Then I can identify what its inputs are, make those parameters to the function, and then I can just call the new function from the side of the extraction. And I'm guaranteed this does not change the program. I'm even guaranteed that if I use this new extracted thing function somewhere else, it'll behave exactly the same. And this guarantee is really nice to have when refactoring. Now, referential transparency only works when your code is pure and immutable. If there's impurity and mutation going on in your code, referential transparency doesn't apply. So without referential transparency, it's much harder to safely rip out and move chunks of code during refactoring without reading it all very carefully to make sure that the refactoring won't change something. So here's an example. We're doing a select off of a list, and we're adding the result of calling getNumber to each list element. If we do a little refactor and we extract the call to getNumber out and we give it its resultant name, we have no guarantee that we haven't changed the behavior of this code. This is because we don't know if getNumber returns the same value every time because it's impure. If it returns something different, we've just broken this code. Now, if everything was immutable and pure, getNumber would always be returning the same number because it's always being passed the same thing, which is nothing. And this would be a safe refactoring that wouldn't change behavior thanks to referential transparency. So you may have heard the functions as first-class values soundbite before, maybe even at the beginning of this very presentation. Well, what it actually means is very, very simple. It's basically saying you can treat a function just like any other value in the language. And this means being able to assign it to a variable in a mutable language or name it with a binding in an immutable one. In fact, we've already seen an example of it with our concat function from before. Now, being a first-class value, functions must be able to be passed to other functions and returned from them. So the only odds binding that's up on the slide is an example of passing a function as an argument. We're passing that isOdd function to the list filter function as an argument. The list filter function will then use it to filter the list down to only odd numbers. First-class values should also be able to be returned from functions. So the list filterer function is an example of a function that itself returns another function, and that function will take a list and filter it using that predicate function that was initially provided. Functions as first-class values are very common in modern programming languages. C#, JavaScript, C++, F#, they all have this core functional programming characteristic. Now, if the term currying makes you think of a delicious meal and not functional programming, then this slide is for you. The simplest form of a function is one that will take a single input parameter and return a single output result. So the type signature for such a function is up on the slide. This function takes an integer and returns a string. Currying a function is the process of taking a multi-parameter function and changing it so that it is in this simplest form, a function taking a single parameter and returning a single result. So let's take a look at the example of an add function. The add function takes two integer parameters. So obviously that's not its simplest form because it takes two things, not one thing. We needed to take one thing. So let's take a look at the type signature of the curried version of the add function. We can see that it now takes a single parameter. It takes one integer. However, it returns one thing, and that thing is another function. And that function takes the second integer, and it returns the result. Now, in F#, all functions are curried by default. So our letAddXY function is actually shorthand for this add function, where you can explicitly see that the add name is actually a function that takes a single x, that returns a function that takes the y, that then adds the x and y together and returns the result. Now, in that function type signature, we don't usually show those parentheses that are there. We usually write the type signatures without them. And this is because those function arrow operators are right associative, which means the brackets go around the second and the third integers. If it was left associative, they'd be around the first and the second ints. Now, the currying name, if you're wondering where that came from, comes from an American mathematician named Haskell Curry, and it's not the food, unfortunately. The programming language Haskell was also named after Curry, and Curry was best known for his work in combinatorial logic. Partial application uses curried functions in order to partially call a function. And this means you can call a function and not pass all the parameters, and you will, thanks to currying, get back a function that will take the remainder of those parameters. So let's look at the example of our add function again. We can call it normally with two parameters, like 2 and 3, and we'll get back the value of 5. But we can only call it with a single parameter as well, like just 1. And we'll get back a function that takes the second parameter and adds 1 to it. So by partially applying the add function, we've actually built ourselves a little increment function. And these partially applied functions, like the increment function, are just like any other function. There's nothing special about them. So we can call it with, say, a value of 2, and we'll get back a 3. Now, partial application is very useful because what it lets us do is compose functions together in nice, readable ways. So let's work through an example where we'll create a list of numbers from 1 to 10, and we'll filter that down to only odd numbers, and then we'll convert all of those numbers into strings. So let's start by creating a list from 1 to 10. So the square brackets, remember, is how we create a list in F#, and the dot dot gives us the range of numbers from 1 to 10. So the first thing we're going to do is we're going to partially apply the list filter function with the isOdd function to create a filter by odds function. So let's look at how this works in detail. We can see the type signature on the slide for the filter function. It takes the predicate function a to bool, and what that little function is going to do is check each a and see whether it's something we want to keep, so true or false. The second parameter it's going to take is the list of a's that we want to filter, and it's going to return the filtered list of a's. Now, when we pass that isOdd function, we're going to make those generic type parameters concrete. So the a becomes the int. Now, we've only passed one parameter to this two-parameter function. So what we're going to get back, we're going to be partially applying it. We're going to get back a function that takes a list of ints and returns a list of ints. So it's going to take the list we want to filter it by only odd numbers, and return a new list. So the next thing we can do is create a convert list to strings function. And we're going to do that by using the list map function, and we're going to partially apply it with the toString function. So the map function is like a link select. So by only passing that toString function to the list map function, we're going to get back the rest of the function, so the parameters that we didn't apply there. And that function is now going to convert a list of ints into a list of strings for us. Let's walk through how that works. So on the bottom of the slide, we can see a type signature. So the top line there would be the type signature for map. We can see the first parameter is a function that will convert an a into a b. So that's our mapping function. The second parameter is a list of a's, and it's going to return a list of b's. So it's going to convert each a in the list into a b and return it. So when we pass our toString function, we're going to make those type parameters concrete. So a becomes int and b becomes string. Then, because we're only passing one parameter, we're going to get back a function that takes the rest of them. So now we're getting back a function that takes a list of ints and will return us a list of strings. So now we've got our convert list to strings function. We can compose all of the three things together that we've got now using the pipe operator, which is the pipe and greater than operator up on the slide. And this pipeline operator is going to call the function on the right-hand side of the operator with the value on the left. So it's basically feeding the result of the left into the thing on the right. And this allows us to easily read the code from left to right. You can think of it a little bit like a Unix pipe. So what we're going to do is we're going to feed our list of 1 to 10 into our filter by odds function. we're going to take the output of that function and we're going to feed it into convert list to strings function. And then finally, we're going to get back our list of odd numbered strings. Now, we've written this out extremely verbosely so that we could walk through that partial application very carefully. But in practice, we'd write the code like this new snippet at the bottom left of the slide. So we can see partial application allows us this nice readable style that is very reminiscent of fluent style syntax in C#, except that we can do it anywhere with any functions and not just the extension methods that happen to have been provided for a particular type. Partial application and function composition is one of the reasons why functional programming makes it really easy to write code that composes together in nice readable ways. Now let's switch gears and talk about algebraic data types. Algebraic data types are named after their basis in mathematics, but that doesn't mean they're complicated. If you know addition and multiplication, you'll be on board. There are two types of algebraic data types, product types and sum types. Let's first look at product types. Product types are those that are made up of multiple other types of values at the same time. You can think of them as like an AND of types. So record types are product types, and tuples are also product types. So in any instance of the myRecord product type that's up on the slide, we have a byte, a bool, and a second bool. Now they're called product types because the total number of possible values of a product type is the product, or the multiplication, of its parts. So for myRecord product type, it can have 1,024 possible values because a byte has 256 possible values, and a bool can have 2 possible values. So 256 by 2 by 2 is 1,024. And this is why the syntax for tuples in F# uses that star operator, like you can see for that myTuple product type, because tuples are product types. So here's what it looks like to create a record type and a tuple in F#. We've seen it before. It's pretty simple. Remember that we must set all those properties up front because these things are immutable. Product types are kind of normal. You can make something that looks like them in pretty much every language. But some types are something that aren't widely available outside of FP languages. Some types let us define a choice between other types. You can think of them as the OR of types. So while product types were this and that, some types are this or that. F#'s version of some types are called discriminated unions. On the slide, we can see a definition of a discriminated union called mySumType. It defines 3 alternatives, a byte, a bool, and another bool. Now, some types are called sum types because the total number of possible values of a particular sum type is made by adding up, so summing, the number of possible values of its parts. So in mySumType's case, it has 260 possible values because a byte has 256 possible values and a bool has 2. So 256 plus 2 plus 2 is 260. Now, some types are super useful at modeling a closed set of alternatives. So here's an example of using an F# match expression to determine at runtime which alternative we have at hand. And you can think of a match like a very fancy switch statement. So what's great about some types is that if you add another alternative to them later, the compiler will emit warnings at all the places in the code where you need to add new code to handle that new alternative. And that's really good for code maintainability. Here's how we create values of this sum type. We can use those case constructor names and pass them what they contain. So for example, we create value 1 by passing 127 to a byte constructor. And we create value 2 by passing false to a bool constructor. So to create a value of mySumType, we must use one of those constructors. And that's how we pick between which alternative we want when we create values. So let's talk about value semantics. Types behave with value semantics when 2 different instances of the same value can be compared for equality. So for example, in C#, strings and integers have value semantics. You can have 2 instances of the same string in memory, but if they're compared with equals, they're considered to be the same. However, in C#, when you define new classes, they behave with reference semantics and not with value semantics. And this means you can't compare 2 instances of a class with same values in its properties and see if they're the same. If we look at the example up on the slide, we've got a class that defines a first name and a surname property. And if I make two instances with the same names and compare them with equals, they'll be considered to be unequal. And this is because reference semantics are enforced. These are two different instances in memory, so they're considered to be different. Unfortunately, in C#, it's kind of difficult to get value semantics for classes. You need to override equals and the two equality operators, override get hashcode, and implement equatable. And worse, you need to maintain that implementation so that if someone adds a property, they need to be very careful that they update their comparisons and in their equals implementation and also in their get hashcode, because if they don't, you're going to end up with a very subtle bug. In F#, you get value semantics for free on both your record and union types. So if we define a full name record type, create two instances with the same values, we can compare them for equality for free. And the compiler will generate the necessary comparison code for us and keep it up to date as we add and remove properties. So where is value semantics useful? Well, tests become trivially easy to write because you can simply compare entire data structures for equality. There's no need for manually asserting each property or using reflection to make some sort of deep equals function. So if we look at the example we've got up on the slide, we can imagine we're writing a test for some sort of name generator function that takes a list of first names and a list of surnames. And we want to make sure that it's generating the right full names. We can generate the names by calling the function, and then we can simply do an equality comparison on the expected list of names. F# lists, created by using those square brackets, have value semantics as well. So you can compare two lists for equality just by using equals. In other languages, you might need to assert the list length and then each item in the list, or resort to a library that does that for you. In F# and other functional languages, value semantics makes it super easy to just assert that an expected result equals an actual result in your test just by using equals, and that's it. Now, in imperative languages, doing something repeatedly requires writing a for or a while loop. These loops, by definition, mutate state. Let's take a look at a simple snippet of code that sums up integers in an array. We use a basic for loop, and each time around the loop, we mutate the value of index, and we accumulate the sum by mutating the value of the sum variable. And this mutation is what allows us to maintain the state of our loop. So if looping requires mutation, how do we loop in a functional language where immutability is king? And the answer is that we use recursion. Recursion is where a function invokes itself over and over until eventually it stops. And that over and over aspect is what makes it a suitable substitution for mutable loops. So let's look at how we could implement summing using recursion instead. On the slide, we've implemented a recursive function in F# called sum. Let rec are the keywords that we use to tell the compiler that this will be a recursive function. So the parameters for the function are the array and the index value. The body of the function simply checks to see whether the index value has passed the end of the array. If it hasn't, we're going to read that current array element, and we're going to add it to the number returned from recursively calling ourselves. But when we recursively call sum, we pass the next index in. And this is the important part. Unlike normal loops where we use mutation to maintain state, when doing recursion, we pass this new state forward into the next recursive call. And this way we can change state without mutating anything. Now eventually that index will fall outside the array and we need to stop recursively calling ourselves. So at that point we just return 0. Every recursive algorithm has this particular feature, a branch where under some condition we will stop recurring, because if we don't, we'd end up with an infinite loop. So let's see how this evaluates on the right-hand side of the slide. We're going to start the first call by passing in the 0 index and an array of numbers from 1 to 3. So that syntax with the square brackets and the bar is how we create an array in F#. The first step will give us 1 plus the recursive call to the next step. And you can see that the index we're going to pass to that recursive call is 0 plus 1. And I'm going to use colors on the slide so you can keep track of these recursive calls. So the blue step is going to result in 1 plus 2 plus another recursive call. And this gets a new index of 1 plus 1. And this results in 1 plus 3, 1 plus 2 plus 3, plus another recursive call. And the index passed to that will be 2 plus 1. Now that recursive call is going to hit the end of the array. So it's going to stop recurring, and it's just going to return a 0. So we end up with 1 plus 2 plus 3 plus 0, which gives us our value of 6. So see how we've been able to perform a loop without any mutation at all? That's pretty neat. Now there's a few practical issues with this particular implementation, but we'll resolve those in future slides. Recursion as a concept is not just useful in functions, it's also useful in data structures. In fact, we've seen a recursive data structure before, the immutable linked list. Now just like that dude's chin, you can see a repeating structure in this linked list. The linked list will contain itself until at some point it stops, just like our sum algorithm. So to work with these sorts of immutable recursive data structures in FP, we use recursive algorithms. So let's look at our sum function again, but this time we're going to use an immutable list instead of an array. So on the slide, we've defined a sum function that takes a list. Our function uses a match expression to inspect the structure of the list. And this is where F# match expressions become much more powerful than switch statements. They can decompose data structures into their parts. So in this example, we have two cases. In the first, we're matching against a list that has an element, which we're calling the head, and the rest of the list, which we're calling the tail. Remember the structure of a list. It's made up of an element and a reference to another list. So head is the element, and tail is that other list. In the second case, we're simply matching the empty list, which will indicate the end of the list. So in the first case, we're going to add that head value to the value returned from the recursive call to ourselves. Now when we call ourselves, we're going to pass in the tail of the list. And this means the next iteration of the recursion will pick the head off the tail, which is effectively the second element in the list, and so on and so forth. And that recursive looping will continue until the end of the list, upon which we'll stop recurring and we'll just return 0. So let's look at the execution of this function on the right-hand side of the slide. We're going to call the function with a list of numbers from 1 to 3. In fact, this square brackets ... syntax is just shorthand for this longer syntax on the second line here. So when we write the list out this way, using that double colon cons operator, we can see that recursive structure more easily. So in the first step, we decompose the head off the list, which is 1, and we add it to the recursive call to sum. And we're going to pass in the rest of the list. So that would be our 2 cons 3 cons empty list. And we're going to do it again and again until eventually we hit the end of the list, in which case we're going to return 0. Then we've got 1 plus 2 plus 3 plus 0, and that equals 6. Let's take a look at another function we can write recursively, the filter function. And it's going to take a predicate as its first parameter, which is itself a function that will take a list item and figure out whether or not it's something we want to keep. The second parameter, of course, is going to be the list we want to filter. So the implementation is actually quite similar to sum. We're going to match on that list to extract the head element and the tail of the list. Then we're going to use the predicate function to see if that head value is something we actually want to keep. If it is something we want to keep, what we're going to do is we're going to add it to the front of the list that's returned by calling ourselves recursively. And we're going to pass the tail into that recursive call. Now, if it's not something we want to keep, we're just going to ignore it, drop it on the floor, and do a recursive call directly and just return whatever that returns. So let's see how this executes. Oh, and I should say at the end of the list, we just return an empty list. So on the right-hand slide, we're going to see how we execute this algorithm. So we're going to call the filter function, and again, we're going to expand that list syntax out so that we can see that recursive structure. So the first call is going to result in 1, and we're going to keep it because it's an odd number. And we're going to add it to the front of the list that's returned by calling filter again. So that's that double colon cons operator. So you can see we're passing the tail into that recursive call, so the tail being 2 cons 3 cons empty list. So the next step is going to drop 2 because it's not int. It's not an odd number. So we're going to just keep the same. We're going to have 1 cons 2, the recursive call. But now you can see we've got another tail, the next tail, which is just 3 cons empty list. Another call, we're going to end up with 1 cons 3 cons filter and filtering on the empty list now. And that is going to return the empty list. So now we end up with a list of 2 items, 1 and 3, which are all our odd numbers. And that's pretty cool. Now, I mentioned there was a slight problem with these recursive algorithms. Let's see how they execute on the stack. So here's the sum function again, and we can see the first function call in that first stack frame. So we're going to call into the first recursive step, and the next, and the next, and the next, until eventually we get to the end and we're going to pop back down the stack, returning as we go, and eventually we get our value of 6. Now, unfortunately, as you can see, the depth of the stack scales with the size of the list that we're recurring over. I love that GIF, man, it's so good. This is obviously a problem because if we have massive lists, we could very easily blow our stack and get a stack overflow exception, and that's obviously not something we want. So when you call functions normally, the stack is used to keep the value of your variables so that when you return from a function call, you can continue from where you left off. Now, if you look at the definition of the sum function that's up on the slide, you can see that after we do our recursive call to sum and we return from it, we're adding the head to that accumulated value that we get back from the recursive call, and we're returning that. So we're using stack space to store that value of the head so that it's there for when we get back from our recursive call so that we can add it to the result and return it. So how can we avoid using the stack to store state during our recursive call and therefore prevent stack overflows? And the answer to that is to use a specific type of recursion called tail recursion, and this is a type of recursion that can be optimized by the compiler and runtime to use no stack space. A tail recursive function is one that will simply return the result of a recursive call. In other words, it does no work after the function call returns. So let's see how we could rewrite our sum function using tail recursion. So this new tail sum function on the right-hand side here takes a new accumulation parameter, and it does the same pattern match that we did on the list before. So we extract that head off the list and have the tail. But this time we add the value of the head to the value of that new accumulation parameter, and we pass that to the recursive call to tail sum along with the tail of the list. And the value of this recursive call is immediately returned. And you can see that no work is being done after the recursive call at all. We just return its result directly. And what this means is that any state that we're storing on the stack is not required after we've done that recursive call because we're not doing any more work after it. And this allows the compiler and the runtime to perform a tail call optimization, where either that recursion is rewritten into a loop by the compiler, or the runtime will perform a tail call instead of a regular call. And a tail call will just overwrite the current stack frame so that the stack doesn't grow. Now, our tail sum function now has this extra parameter on it that our callers don't really care about. So we usually nest this function inside another function and seed that accumulation. So you can see that we're seeding the accumulation with a parameter, we're seeding it with a value of 0. So in that first iteration of the recursion, we'll be adding our list head to 0. Let's see what tail recursion looks like on the stack. So we start with calling our sum function with a list of 1 to 3. And this is going to call tail sum, and it's going to start that accumulation with 0. It's then going to call tail sum recursively with a new accumulation of 1 plus 0. So notice how we didn't get a new stack frame there. We just overwrote the current one. This is a tail call in action. So the next step is going to do another tail call, and this time we're going to be adding our head value of 2 to our new accumulation of 1. Again, no stack frame is required because of the tail call. So this step now is going to add our head of 3 to our accumulation of 3, and the next step will hit the end of the list, so it's simply going to return the accumulation, which is now 6, and that is going to return to the original caller. You can see that by writing our recursive function using tail recursion, we've eliminated the stack overflow problem that regular recursion can run into. And we've done this by passing all of our state forward into the next function call, instead of relying on the stack to store some state for us. If we contrast this to the mutable version of sum, we can see some similarities. In the mutable version, we're storing our accumulation state in a mutable variable, and we mutate it on each loop iteration. In the immutable tail recursive version, we're also accumulating state, but we're passing that state forward into the next function call rather than mutating it in place. So let's look at another function we can implement using tail recursion, reversing an immutable list. This function looks very similar to our sum function, but instead of doing addition, we're going to concatenate to a list. So you can see we've got an accumulation parameter, which we're going to start on that last line with an empty list. Then inside tail reverse, we're going to pattern match the head off the input list, and then we're going to add it to the front of that accumulation list. That new accumulation is then passed to the next recursive call to tail reverse, and eventually we're going to run out of list items. And when that happens, we're going to return the final accumulation value. Again, see how we're never doing any work after doing the tail recursive call to tail reverse. We simply return its value ourselves. And this ensures that we're tail recursive and we won't overflow on long lists. Now you can see the pattern of what happens to list and accumulation at the bottom of the slide. You can see as we tear down the list, we build up accumulation. In fact, it's very much like that post-it notes GIF. We're just taking off the front of one list and adding to another, and the very nature of doing so is what reverses the list for us. Now, we previously implemented a recursive filter function. Now let's do the tail recursive version. Again, a very similar form of function. We have an accumulation parameter, which we're going to start out with an empty list. We're doing a pattern match to extract the head, but this time we're going to use that predicate function to test if we want to keep that head value or throw it away. And if we want to keep it, we're going to add it to our accumulation list. Otherwise, we're just going to ignore it and just return the same accumulation list. And we're going to pass that new accumulation list into our tail recursive call to ourselves, and we're going to keep going. And eventually, we're going to run out of list, and at that point, we have a new wrinkle. Here, instead of returning the accumulation directly, we're going to reverse it before we return it. Now, why are we doing that? Well, let's have a look at how our list and our accumulation build up through that recursion on the right-hand side of the slide. Notice how we're accumulating the list in reverse order as we're reading through it. We exploited that behavior in our reverse function in order to reverse a list, but this time we don't actually want to reverse the list. Filter functions typically don't change the order of the list that they filter through. So to counteract the reversing of the list, we re-reverse it before we return it. Now, you may have recognized a very consistent pattern in all of our tail recursive functions with lists. Let's look more closely at the similarities. All three have an accumulation parameter that starts with a base value. All three extract the head off the list. All three combine that head value into the accumulation in some sort of way, and then it passes that new accumulation forward into the tail recursive call to itself, and also passing in the tail. All three will return the accumulation when they reach the end of the list. Turns out that this sort of algorithm can be generalized into something called a fold. A fold looks like what's up on the slide, so let's walk through that carefully together. The fold function takes another function, which we're going to call combine. This combine function takes an accumulation value and one of the items from the list, which we're calling t, and it's going to return a new accumulation value. The second parameter is going to be our starting accumulation value, and the third parameter is the list we're going to go through. And the return value will be our final accumulation result. So let's see how this fold function implements all those three or four common elements that we identified before. It has an accumulation parameter that we pass with some sort of base value. It extracts the head off the list. It then combines that head into the accumulator using the combine function, and then it passes that new accumulation into the tail recursive call to itself. And once it's reached the end of the list, it will return that final accumulation. Now, the fold function is named fold because you're taking a list and you're folding it up bit by bit into a single accumulation value. And I like to visualize that in my head as if your list was a long piece of paper and you're folding it into squares, and at the end you end up with like a stack of paper. All right, so now that we've extracted all that common logic out into a new fold function, let's see how we can implement our previous sum, reverse, and filter functions using our new fold function. So starting with our sum function, we're going to first combine our combine function, and that's going to take an accumulator and combine it with an item from the list. And so simply in this case, we're just going to do an addition. We're going to add the two together, and we're going to return that. So now we've got our very simple combine function, and we can simply call fold, pass in our combine function, our starting value of 0, and the list we want to sum up. And that's it. It's done. How about reverse? Again, we define our combine function. This time we take the item and we add it to the front of the accumulation list. We then take this combine function, we give it to fold, we give it our starting accumulation of an empty list, and we give the list to fold over, and done. We've got a reverse function. What about filter? Well, again, we define our combine function. It just uses the predicate to see whether we want to keep that particular item or not. If we do want to keep it, we add it to the front of the accumulation list. Otherwise, we drop it on the floor and return the same accumulation list. Then we call our fold function. We pass in our combine function. We pass in the empty list to start our accumulation, and we pass in the list we want to filter. But here, remember, we're also doing a reverse to make sure that we get back our original list ordering. And boom, we've just used a general fold function to implement our 3 tail recursive functions. So while recursion is crucial in functional programming as a way to loop over data, you can see that most of the time we can use folds to perform that loop for us. One time that you might want to still use manual recursion is if you want to quit your looping early. Our fold will always recur to the end of the list. So if you only want to recur a certain way and then stop, then you might still want to write recursion yourself. Folding isn't new. In fact, you've probably used it before in your favorite language and perhaps not even realized it. Folding in C# goes by the name aggregate from the link extension methods. In other languages like JavaScript, it's sometimes called reduce. Most languages have an implementation of fold for their collection types, so you don't need to implement it yourself like what we did. You can just use what's built in. All right, so let's wrap up all the FP jargon that we've gone through today. We started by talking about immutability and how FP languages make it easy to work with immutable data, and we looked at how immutable lists were created. We then looked at bindings and saw how they differed from variables in that they give a name to a value and that they don't change. We looked at pure and impure functions, pure functions being ones that always return the same result given the same input and don't mutate their inputs, nor do they depend upon global mutable state. We saw how immutability, bindings, and pure functions allow us to substitute names for values with a concept called referential transparency. We also saw how referential transparency allows us to refactor code more easily by allowing us to safely extract and move code around. We touched on how in FP languages and in many modern languages, functions are treated as first-class values and can be passed to other functions and returned from them. We looked at curried functions and how this enables partial application of functions, where we can pass only some of the parameters and get back a function that takes the rest of the parameters. We compared 2 different types of algebraic data types, product types and sum types. Product types being the combination of more than one value, like a record type or a tuple, and sum types allowing us to model the alternative between different types. We walked through value semantics and we saw how it offers the ability to compare 2 instances of something that have the same values easily, and this makes our tests much easier to write. We then spent a bunch of time exploring recursion, and we implemented sum and filter recursively. And then we discovered that we've got a Stack Overflow problem in our regular recursion, so we introduced tail recursion so that we could stop using unbounded stack space and implemented sum, reverse, and filter tail recursively. And finally, we extracted all our common tail recursion logic out into a general fold function, and we simplified our sum, reverse, and filter functions. So if you liked what you saw today and you're looking for some more, I highly recommend checking out Scott Lashen's website, F# for Fun and Profit. He walks through FP techniques and the F# language in a very approachable way, so I do recommend you check that out. Mark Siemens' blog also has some really good content. He's been going through a lot of functional fundamental patterns recently, so check that out. If you liked this talk but you thought it was just getting good at the end, then you might be interested in seeing the sequel talk that came out before this one at NDC 2017. In that one, I talk about functor, applicative, and monad FP patterns. So the video recording and the slides are online, thanks to NDC, so you can check that out if you want. And of course, there are other people here at NDC Sydney giving talks. Don Syme, who's the creator of F#, is giving a talk tomorrow about F# code that he likes at 11:40, unless the schedule has changed, and I don't think it has. And Matthias Brunderwinder is giving a talk tomorrow at 1:40 about where he'll model Dungeons & Dragons rules with F#, and I'm definitely going to be in that one because that sounds sick. So if you're the sort of person who likes to learn things from principles and fundamentals, I'd suggest you check out Haskell Programming from First Principles as a textbook. It starts from scratch and it builds up very slowly. It has a very gentle learning curve. It's a very big book, so it might be a gentle learning curve, but it's a very long one. But by the end of it, you'll be eating monads for breakfast and it won't be a problem. It's actually a very good book. But if you're the sort of person who just likes to get in and get their hands dirty quickly, F# for front and profit is probably a better place to start. So thank you for listening. I hope you enjoyed the talk and you got something out of it. The slides will be available up on online at the link. And NDC obviously makes these talks available as videos after the conference. So if you felt like you needed a pause button so you could just stare at the code for a bit, check out the video when it comes out. We do have time for a few questions. So if there's something that confused you or you have some question about FP, feel free to pop up your hand and I'll do my best to help. Thank you. Any questions?
Please explain what is just monoid is a category of interfunctional.
Oh, there. I got the troll question from not my friends. I will say that you don't actually have to understand any of that to understand monads. They're actually not that complicated when you dig into them. So I think probably, oh, how would I explain a monad in like a couple of words? I think probably the best like metaphor for one that I heard was one that John told me in the past. Is a monad is like a type amplifier. So if you think about it, you've got a particular type like a string. If you want to give it some sort of additional behavior, so amplify the type, a monad is a way you can do that. So for example, like the option type, something that models the absence or the presence of something, you can have an option of string, so you're amplifying a string to have the ability to be there or not. Or a list is also a monad, so you can amplify a string in a list of strings so you can have more than one, or 0 to 1, 0 to many strings. And there are many more cases where you can use them. I find the best way to understand a monad is not to actually try and think about it from an abstract perspective, like what is it? It's easier to look at all the concrete ways you can build monads, and then once you've seen like a list is a monad and an option is a monad, and async is a monad, then you start to see the common pattern between them and you realize it's actually not that complicated. So I didn't directly answer your question, but hopefully that was enough. Yep.
So you talked about properties or types. We have to define all the properties at the same time.
Yep.
If you don't have that option, or in programs where you don't know all the values ahead of time, how do you go ahead and define this?
So if you're in a case where you basically want to, let's say you've got a record type that has a whole bunch of properties on it and you want to be able to only initialize some of them, what you probably end up doing is model the fact that at some point in your program you don't have all of the values, you only have some of them. So you might create a new type that has, for example, only the values you have at that point in time, and then when you get the other values, you then might take the values off that particular record and put them on the new record. Or if you might have all of the values at any point in time, you might make another record type which has option whatever type for all of the properties, and that way you can say, well, I have these ones and I don't have these ones. And then at some point in the code, if you're using that final record type that must have everything, you've got to write some validation code. And that's not a functional thing, that's just programming. At some point, you're going to have to write some code to check, do I have this, do I have this, do I have this? And at that point, you transform from one type to the other. So the nice thing about the record type is that because it forces you to initialize everything, it actually also forces you to model what's happening in your domain more accurately. So it's pretty easy to get sloppy in a language like C#, and we can just use the same type for both. But then at certain points in the code where you expect everything to be there, you don't have a guarantee, and it's easy for bugs to slip in. But when you're using an immutable type like a record type, you're forced to make that explicit. So at some point in the code, I don't have everything, and then at some point in the code, I will have everything. That's explicit in the types, and it means you don't have to write all this null checking stuff that you do in regular C#, which is pretty nice. Yep.
Just regarding pure functions and impure functions, I guess, is there certain implicit rules that you just say, oh, this looks like a pure function, not? Or is there actual compiler kind of checks to say, hey, you just define this as a pure, you can't do this in the function?
Yep. So the question was about when you're writing a pure function, will the compiler give you any way to say this must be a pure function versus this doesn't have to be a pure function? Well, that depends upon the language. So in F#, no, there's no way to write, there's no way to get the compiler to validate that a particular function is pure, which is a shame because it'd be nice. But F# is a .NET language, so it participates in an ecosystem which is extremely mutable. So mutation is kind of expected in F#, and so you try to write most of your code purely, and then it's sort of based on trust there. So, but there are languages which force you to be pure. So Haskell is one of those. Everything you write in Haskell has to be pure, and impurity is managed through monads and I/O and stuff. So you can obviously still do side effects in Haskell, but the code that you write must be pure. And if you literally can't mutate anything. There's no like mutation operator. There are types that let you do something similar to that, but yeah, they model it a very different way there. So if like guaranteed purity is something that you want, and it's something that I want, then Haskell's pretty good like that.
So is there like a suffix you need to provide in F# for the function name to say, hey, this is pure, so you can mess around with it and safe with it? Or do you actually just tend to find yourself always hitting into the function just to trust whether you can make changes?
So the question was, is there like a convention that helps you know whether a function is pure or not in F#? Not that I've come across. Usually, if a function is just using F# types, so things like F# lists, sets, maps, and record types and sum types, well, those are all immutable. So if you can see in the type parameters that it's using only those types, then you're pretty much sure that it's not going to be doing that, because hopefully the people who are writing the code have done the right thing. But of course, there's nothing stopping someone from using datetype.utc now and stuffing it up. So that is something you've got to watch out for. So on my projects, we typically catch those things at code review time. So if I'm reviewing a PR and I see someone slip in a dirty little datetime.utc now in there, I'll be like, no, we got to pass that one in. So yeah, unfortunately, the tooling doesn't help you with that. And I haven't seen a convention, because again, a convention, they're easy to break. So it's not really a guarantee. Yeah. John?
There's actually impurity of behavior as well, right? There's nothing that prevents you from launching this line in the middle of the function. And there's no way to catch that in F# anyway. So the type signature doesn't give you quite as much of a strong guarantee as you would like.
No. And that's the sort of the middle ground that F# plays as a language. It is by design a language that sits sort of in between the pure hardcore FP paradigm and the OO paradigm, because it's a .NET language. So that's one of its strengths, and also obviously there's a downside to it depending upon your perspective. But the good thing is that you can just go off and use a bunch of C# libraries if you need to. So the question was, what do I think the downside of functional programming is? I think, to me, the biggest downside is that most people don't know it. So it's very unfamiliar to people who haven't seen it before, and it kind of scares people off. So I think to me, that's probably the biggest hurdle that it has, and the biggest disadvantage is that if I write a piece of FP code, I can't just give it to any developer and they'll immediately be able to grok it like pretty much every other language. And I think that's just more of a function of history than anything else. Most people, when they go through uni or they teach themselves online, start with an imperative, mutable, OO-ish language, and that's just where they come from. Other than that, sometimes that, like what I was saying before about being forced to model things correctly, sometimes you just want to hack together something quickly just to prove a concept. And being forced to handle every case correctly like you'd want to do in production code is painful. It's like, I'm just hacking together something to see if something kind of works, or to just rip some data that I know is a certain way. Yeah, okay, this field might be missing, but I know it's not because I can view the whole file and I know it's not missing. So that sort of stuff sometimes when you've got a strict type system can get in the way, and you'll be like, oh God, I don't want it, whatever. In F#, that's not so much of a big deal, because you do have the ability to do all the .NET stuff and cast your way out of things and do mutation if you want to. So like prototyping quickly isn't too bad in F#, but in Haskell it becomes a little bit harder, because it will try to force you to write good production code that's got all the properties of good production code, but maybe you don't want to write that right now because you're just trying to do a little prototype or something, then it's painful. Cool, that seems like it. So thank you for coming. Enjoy your lunch.